go. All right. Welcome to the last round of easy, effective, efficient GPU programming in Python with PyOpenCL and PyCUDA. What's going on? First of all, I'll tell you a tiny bit about PyCUDA. It's not just that it disliked PyCUDA. It chose to send PyOpenCL. Then I have a little bit of entertainment that I created that I thought I should show you guys, but it's not to be taken that seriously. It is serious. It's an entertainment. Then I'll give you a glimpse of my own work on top of all this stuff involving finite elements and discontinuous Galerkin, and that shall conclude my part of this summer school aside from the lab. Speaking of the labs, if you were in lab 1 yesterday, I think for the solutions at the end of the lab, I think I posted the wrong tarball. I think just more problems. So to fix that, I'll post solutions at this URL, which you will later on be able to get from the slides from the PASI webpage. I'll try to remember this to do before I leave for the airport. And if you're on the same band, please remind me. All right. So let's get started. PyCUDA. Why not start with a code example? I hear you guys like code early in the morning. This looks actually very, very similar to the PyOpenCL version of things. So instead of PyOpenCL, we use PyCUDA. For PyCUDA.driver as CUDA. I'll show you why it says driver here in a minute. Then instead of creating a context and creating all this other junk, we just import PyCUDA.autoInit, which chooses something, some device. Also, we need PyCUDA.compiler. As usual, create some array of single precision floating point numbers, allocate memory for it on the device, copy the stuff over. This is synchronous copy, this often conversion. So much for preparation. Then, before it should look even more familiar, then there's the compute kernel that we feed to an object called a source module that we get out, in which we can get a handle to the function twice, coded up here. Well, like in the PyOpenCL example, what happens is that just multiplies a bunch of numbers by 2. And we then simply call that function with a given block size. And well, in this case, we default to just having one block, but obviously in a real computation you might want to have more than one block. Make an empty numpy array to transfer results to, transfer out, print the 2, and lo and behold, one will be the double of the other. Not too terribly interesting if you've seen PyOpenCL, just pretty much more of the same. Likewise, this array facility that I've discussed yesterday in PyOpenCL exists in PyCUDA too, so GPU array to GPU stuff 2 times that and get it back out, and that is precisely the same thing. And it does all the other stuff, including reduction and element-wise computations. So in that sense, the two packages are really very, 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 very similar. On top of that, something that is so far only in PyCUDA is interacts on top of a package called scipy.sparse. Lets you do sparse matrix vector computation based on the work by Nathan and Michael Galerkin. And actually, I think by their license I was allowed to include part of their code. If I wasn't, please complain now. And one neat thing that it does, it has a conjugate gradient solver. And how many of you know how to code conjugate gradients? Somebody else. A bunch of vector things, and then inner products. And you make a decision of whether you could have converged based on the inner products, right? So that's or based on the result of an inner product, which gives you the norm of the residual, and that has to travel back to the CPU to give you to enable you to make that decision. So waiting for that transfer to complete might hold up the rest of the computation. A neat trick that this does, I think, implements is it fires up the transfer to the host, meanwhile keeps computing because more iterations rarely hurt. And then as soon as the the residual arrives on the host, then does the convergence check. And then if you can tell, okay, we've gone maybe a little bit further than we meant to, then we can cut off the computation and return the result. But worst case is gotten even a little bit further down than the residual that we mentioned. Okay, this might be useful for you if you're looking for this kind of stuff. It uses this packeted format that Michael Erland and Nathan specified. They tell me that that's not even the favorite format anymore, so that might need a revamp in the not too near future. But at least it's there and it does work. Right, and if you're coming from PyOpenCL, this might be useful for you to get a picture of if you're used to writing command queues, buffers, programs, kernels, then these are the direct correspondences to that in PyCUDA. But largely, really, concepts map one-to-one, and it's your choice which you program it. Events are actually slightly more general over here. We've been talking about the differences at length, so I don't want to go into that. Another thing that's been underlying both PyOpenCL and PyCUDA is, well, traditionally if you have a compiled code, if you code in C, say, then this is the development cycle that you're used to, right? And the premise of doing all of this from a scripting language is that you can do away with this and you can do away with that, and as a result, you can go through the cycle a lot faster than you would usually do. Now, obviously, on a GPU, that's kind of a dumb idea. There is compiled code. You are compiling. So, we can at least try to pretend that something like that is still going on. And here is this edit run cycle that we're shooting for, and obviously somewhere code needs to get compiled. And this happens precisely in the snippet here where we do feed stuff to the source module in the case of PyCUDA. And the way that we retain the rapid turnaround and make the compilation or most of the compilations go away is by simply caching based on the source code that you're trying to compile. Right, exactly. So in CUDA that was something special because CUDA doesn't come with a C-level source just-in-time compiling. OpenCL, that's part of the standard, so that's pretty much taken care of. But PyCUDA gives you that same feel that you already got in PyOpenCL, just based on invoking the compiler and trying to cache your results so that you don't have to feel the weight even or especially if you're doing the same thing multiple times over. Also, this cache is useful if you're too lazy to cache the results of your automated tuning. You just regenerate all the variants, you zip through them, and you just pull the binaries out of the cache. And since the testing on the GPU is really quick, that goes very fast. What you're usually just waiting on is the second between when you invoke the compiler and when you get the result. So you don't even usually have to implement a cache for the results of your automated tuning thanks to this. And then not too surprisingly, okay, check if it's in the cache. If not, compile it, upload to the GPU and run it. Fair enough. Then, how does it actually work under the hood? What you've been seeing in the CUDA side of your lectures is what's called the runtime API. That gets shipped in a separate install, toolkit, CUDA toolkit install. The driver level interface is actually separate from that, and to some extent the runtime is built on top of this driver interface. PyCUDA uses this driver API rather than the higher level runtime. That causes a few small headaches. By now there are surmountable headaches when you're trying to use libraries that are built on top of this guy here. But the only restriction that emerges from this distinction here is that if you are using a runtime API library, what you have to do is you have to let this guy create the context within which you're working. As long as the runtime API retains control of what context you're in, you should be completely fine.
So, you get back to the
Nothing. You don't do anything. You just don't touch any of the context stuff in PyCUDA. Or wait, is it this way or is it the other way around? only one of the two is allowed to do context management. It might be that you have to let PyCUDA do the context management. I'll look that up and I'll say that in
The
the
reason I say it is this is going to be a common way to use it. I could generate based on the kernel using Rust using the runtime.
Right.
To solve the work.
Right. Yeah. How do you merge that? Was that a question?
It's the same question.
Yeah. Right. Well, it's one of the two. You have to let either this guy do the context management in PyCUDA, uses the context that this guy creates, or the other way around. I can't remember which is the correct way. Does anyone of you remember? Have you done this? Okay, I'll find out and I can tell you later on if you can ask me, or I'll also mention it during class. Right. Okay, and then from the driver API on, it's the same thing. It goes into the kernel driver and then finally talks to the hardware. Like PyOpenCL, PyCUDA is licensed under the X Consortium MIT license. So do whatever the hell you want as long as you don't come suing me. More or less. Actually, don't use my nature advertising. And no boost requirement anymore, so NumPy and Python 2.4 should get you started. There is documentation, and you can find all kinds of stuff that you might want to see on my webpage. Alright. That about covers it for PyCUDA. Any questions on PyCUDA other than what we've discussed? Not seem to be the case. All right, then let me show you something entertaining. Right? I think it's entertaining. So nobody likes GPU programming, yet we all do it just because it gets us fast results, right? Obvious idea. Well, let's try and have the computer do it. And conventionally, okay, let's try and do something tremendously smart. Let's have a compiler reason and model and optimize. Alternative way, try all the different ways and pick the best one. Obviously, that's not quite feasible if your search space is enormous like it is, but we can at least try and see how long it would take, and that's precisely what this is about. So, in addition, all of this stuff if you were trying to do it the smart way, what you would have to do is you'd have to model performance in ways that Nvidia would not like to tell you about because it touches parts of the hardware that they don't want the competition to know about. And thus, this is tremendously hard to do if you don't have that insider information. You can always write micro benchmarks to try and find out and characterize, but it is hard. By dumb enumeration, you get around all of these modeling challenges simply by, yeah, question? Of course, yeah, no, you wouldn't want to do a joint optimization on everything. That would artificially explain large. What happens is this is the outside interface. So you specify just a bunch of dimensions and sizes. The sizes have to be fixed at the time when you do the optimization run, and then you specify a number of things that you want defined, and what this here uses is Einstein summation notation. So what we specify here is a matrix product, and we do also specify the memory layouts by converting to linear indices within this expression. Then we give the optimizer a few hints. So we tell them, okay, don't look at solutions that use fewer than 128 threads, and don't look at solutions that use fewer than 32 blocks. That just cuts off little bits of the search space that we know are dumb. And well, in this simple ideal case, well, everybody who writes these smart things find a solution for matrix multiplication, including this one. It does work also for a bunch of other cases, more or less well. So, for example, we'll see a little bit about discontinuous Galerkin in just a few minutes. A few other linear algebra kernels are also well served by it. Finite difference, that's where it starts getting kind of iffy, but at least what I like is that the model that we use to specify it in principle is sufficient to also capture finite difference. So this is it's obviously not a language that's sufficient to capture all that you want to put onto the GPU, right? It's not something that you want to write an FMM in, but it at least covers some well-defined chunk, right? And well, if you want to hack on that, you can the source is public and you can also get it for free. 1,000 lines of Python that just spits out kernels that try and load this into shared memory, try and assign parts of this axis to this grid dimension, and just iterates through all of the two possibilities. I found it entertaining to write. Within the limited scope that it serves, what it really is limited by is, as I said before, the rate at which it can try out kernels. So perhaps with a multi-core machine I can parallelize that too. An explicit non-goal in developing this was very, very, very much the peak of performance. It's probably not going to find that, but if it does give you a starting point to optimize from for a kernel that you wish to write, then I think that's already a fair. It finds things that are just best practices anyway, right? I mean, you can always lie to yourself, right? You can always say, okay, I have this specific kernel, and I'll put specific intelligence that'll force it to find the optimal solution into the optimizer, and then claim, hey, I found an optimal solution for my given problem, so it works. But I didn't try to do too much of that. I focused on having something that enumerates the search space in some way, has the facility to cut off parts of it that we don't like. Yes. Well, obviously, how would it not, right? It stands the whole damn thing. Right. Yes. Okay. That's fair. I mean, there might be little variants that do make a difference that I'm not catching.
Is it easy to tell it that some parts are reused? I mean, it's very often the case that the kind of stuff we want to optimize an FMM or this low order FEM is one thing is reused a lot, and then you bring in another thing.
So for a slight bit, I think I do just a very basic analysis on how often one variable is referenced within one loop that detects could it potentially be reused. It doesn't think about the access pattern, so it doesn't know if the indices are right for stuff to be reused. But if you win this simple check, then you get a part of the search space where stuff gets loaded into shared memory for into So I liked it. I thought it was entertaining to write. If you care, let me know. And with that, we'll switch to for the rest of the talk what I did on top of PyCUDA and what I did for small parts of my PhD, which was trying to bring discontinuous Galerkin methods onto the GPU. What the hell are discontinuous Galerkin methods? Well, they're a finite element method. So you start with a domain, omega, that you assume is a union of disjoint simplices in this case. And what you want to do is discretize a very much time-dependent conservation law on this hash, given that ut plus versions of some plus function equals 0 or equals some source term as long as the source term is not too warped. Examples of these things are useful. One useful example are Maxwell's equations, and we'll see some other examples later on, or there's equations of gas dynamics, stuff like that. What do? It's pretty much the usual finite element dance with one particular difference. So you take your conservation law, multiply it by a test function, integrate by parts, and then comes the one specific thing about the method. Since it's discontinuous, and you get a boundary term across the elements, you're faced with a choice, because while you integrate over the boundary of the element, so there are two elements at that element interface, and they have two different values, because both your test function and your ansatz space or your solution space carry discontinuities. So what do you use along that interface? And it turns out there's a whole rich set of theory that you can steal from that was developed for finite volume methods, and that's the theory of Riemann solvers. And so what you do, since you're solving a conservation law which fits into the theory of Riemann solvers, you just pick one of those Riemann solvers, and for this normal flux here, you simply substitute in that value of the Riemann solver. If you are like us, if you like our particular flavor of the scheme, then well, after you integrate by parts again, such that you get another such boundary term, but there the choice is fixed, so you just choose the interior value. That's sometimes this is described as the weak form. What you get after integrating by parts again, that's the strong form. That has many other names. Same thing. Interestingly, they're different. They're mathematically different schemes that just give. Ideally, if you're solving well, if your solution falls exactly into the solution space, then both solve the equation exactly. So if yeah. That would take you back, except it would give you another boundary. Well, precisely because it does take you back, because it makes writing down this part here trivial.
Drop the boundary term.
No, you don't drop the boundary term. You keep both boundary terms. Because no, it isn't. Because you have choice every time you pick the boundary term. You want to retain. Yeah. So the first time you pick a Riemann solver, the second time you forcibly pick the interior value. So you want something that gives you communication, and that is the Riemann solver, and the second time run. Right. Fine, yeah. Okay. Forget the second integration by parts. The first time you integrate by parts, this boundary term here pops out, and you have a choice for what you put in this boundary term because of the discontinuity, right? It's not clear. It's a discontinuous interface. So there are two values at least to choose, or anything in between. It's not well. No, you see. Imagine two triangles, and the values are like that. Which of the two values do you choose? Gauss's theorem holds that everything is differentiable. If there's a discontinuous interface, nothing is differentiable. So if you were to integrate over a larger domain, what distribution theorem would give you would be the average. Yeah. Again, sorry. I'm not quite sure what you mean. What would I explain in terms of the gap? Okay, let's go to one dimension. Just simply, right? Right?
So granular goal is a sum here over the main.
No, we're just here. I'm just integrating over one element.
Over one?
Just one element, and then I get a boundary term that pops out. And if I was doing it in a distributional sense, then I would get the average between cells for all the boundary terms. If I was integrating over more than the sum. Yeah. But what I'm saying is, instead of choosing that, what would give me the distributional answer, I can also choose in the sense of the equation, because if we're solving a Riemann problem at this interface, I can choose any Riemann solver that I see. So far so good? Okay, we can talk about that later. Okay, so now that I've chosen this here, and this Riemann solver usually gives me, the average plus some other stuff, right? Then I integrate by parts again. So on this volume term, I simply get the same thing back. The only thing that I've gained is junk in the boundary. On the second integration by parts, I have, in principle, another choice, but it wouldn't make sense to introduce yet more freedom, so I just choose the interior value. The value of that is just that it makes this part here simple to write down. If you doing the second integration by parts has this advantage for nonlinear problems, but for linear problems it's perfect. That's a perfectly fine thing to do. Right. Okay. So once we've done that, we're done with formulating the variational formulation of the problem. Then we do the Galerkin thing. We substitute the basis functions and introduce element-wise matrices. Right, and when we do that, it turns out this inner product here that we get for the time in the time derivative, that's a mass matrix. So this is UTMP in sloppy vector form. Then this guy. So actually, since we've integrated by parts again, it's this guy down there at the top. So it's the divergence of the flux function. And there's some boundary stuff. And if we think for a minute about what happens to this mass matrix, we have to invert that over in order to isolate the time derivative. Since in discontinuous Galerkin, these mass matrices are element local, we can invert the mass matrix element by element by element, and just pop those over and integrate that mass matrix into these matrices that we're multiplying these vectors by anyway, which works for simplicial elements or for non-curvy elements. So if you have curvy elements, that would be a function in this way. Complicated things, but for now, what you can do is you just pop these mass matrices over, and you get a fairly simple scheme. So this here becomes simply a matrix that carries out polynomial differentiation. This here is a matrix that carries out this surface integral based on fluxes evaluated along the coordinate. And since we are on simplices here, this and this also reduces to reference matrices or linear combinations of errors. What does my star mean? The star entered up here. I denoted that by I added the star to say there's a choice. It's not just the value of f. This is the Riemann solver for it. Okay. So this sort of normal case.
This might be like double bracket.
Right. Exactly. Well, like the stuff that goes into here is the double bracket or average or some weird sum of this stuff. And we'll see double brackets and something later on. Algorithmically, what we get out of our value of u. And we take two branches. In one branch, we need to compute the flux, differentiate it. That gives us one part of the time derivative. In the other part, we gather the flux across element surfaces, and then we do the surface integration, and that gives us the other part. The nice thing is that this here is the only part that crosses element boundary. All the other parts do not. So as such, it's a rather local method, and these two guys are more or less element local matrix vector product at this level. One matrix vector product per element. So the thinking then is DG might be a good fit for GPUs. Why is that? Well, we've seen that the majority of DG is local. So in that sense, we're a good fit for the deep memory hierarchy. Also, this part here is kind of it's the flip side of that. It's not just that we're local. We're spread along very dense data, locally dense data, per element dense data, and GPUs also love that. So that's another thing. One thing that I forgot to mention up front, DG is typically used as a high order method. So these element-wise matrices have a certain size. Say if you go to fourth order in 3 dimensions, you get 35 by 35 matrices. On top of that, since it is a high order method, we are computationally intense, and that's another thing that GPUs tend to like. So all of those make it seem like a DG on the GPU might be a good idea. What are we shooting for? Well, obviously, we want the whole thing to go fast, right? That's the whole shooting. Second, it would be nice if it was in some sense general, as if we could substitute in at least a linear conservation laws that we know and perhaps a nonlinear one. And lastly, maybe if it was possible to make it easy to use, that would also be nice. We have made a couple of choices coming to this point. We've specialized to straight-sided simplices. Turns out if you were to do this on tensor product elements, it would be a whole different thing. We've looked at that, and I can tell you about it later. And of course, the interesting case is 3D. So if there are decisions to be made, then we've made them in favor of the larger 3D elements. We're shooting for maybe medium order. Why are we shooting for medium and not super high order? Because discontinuous Galerkin methods have a time step restriction that goes as mesh size over polynomial degree squared. So if you dial the polynomial degree too high, then that square kills you. Where at these orders, it's still sort of livable. Right. Okay. Then what makes this business hard? Well, we have basically two matrix vector products, or per element matrix vector products, that dominate the asymptotic runtime. What do those look like? Well, we have 3 matrices that carry out differentiation in the element aligned along the element aligned axes, and we have a bunch of field data. So if you think about that for a minute, that turns into a matrix-matrix product rather, because you're carrying out one matrix against a whole bunch of right-hand sides. So that's usually a more profitable way of looking at the whole thing. And then you have a bunch of geometric factors that, well, you have to take care of, but you sort of ignore.
So,
no, they're not. They're not tensor products. They're so the approximation space that we use is this local Legendre space. And as far as we're concerned, these guys are dense. I mean, they have structure. For example, getting from this guy to that guy is just a permutation. We've tried to exploit that, yet every time that we tried to exploit it,
so
it didn't yield a significant. Well, it made it worse.
The total number is like the technically driven that differentiate together. What's the in terms of polynomial order? What's the complexity of this application of differentiation?
Per element, or
Yeah.
well, it's just one matrix vector product. So it's
I want to know if it's P6 or P.
So NP is P3, so it's P6.
It's P6. That's what.
Yeah. If we were exploiting some tensor product structure, we could get it down. But
Right. So you know,
right, exactly. We're not doing it. And well, let me give away part of the tensor product stuff. Turns out, if you do exploit tensor product structure, you get it's a zero sum game. You lose some flops, like this gets because of the regularity of the computation gets really high flops. The other thing is way more structured, but it doesn't get as high flops because there's more control over it.
when you do test product, how do you that ensure when
Yeah. Right. Okay. So your question answered? Okay. Right. So what do we have to do? Let us get back to this here. Bunch of element local matrix vector products framed as a matrix product. This is for the differentiation, and the surface integral looks pretty much the same way. Here's a question. we can fit either this or that, at the orders that we care about, into on-chip storage. What shall it be? I don't know. And it's a fact of life. On-chip storage is scarce, and it will be for the foreseeable future at least. And we could try and put chunks of both parts of our operating data into on-chip memory, or we could try one part, or we could try another part. How do we decide that question without good heuristics? Not entirely clear to me. I won't answer it right now. Then another question. What do you use for a work decomposition? Well, there's one that's sort of flashing bright red in front of your face, and that's, well, you have all these elements and they contain a nice chunk of work. Why not map one element to one of these work groups, right? Or PASI terminology. That's nice. It's straightforward to implement, and you don't have a granularity penalty because you might have some overlap at the end. On the other hand, you can't fill wide SIMD. How can you not fill wide SIMD? Remember I said the order 4 tet, which is kind of right in the butter zone, has 35 degrees of freedom. If your SIMD group is 32 wide, that's a nice bit of overlap. That's a nice bit of wasted work. You're pretty much wasting the whole second SIMD. That's not a good idea. Also, somehow, well, if you have to make your memory access coalesce, then doing this here is also a bad idea, because you don't just waste processing power, you also waste memory. Depending on which you're more constrained by, either is not very appetizing. Also, you can't really amortize the cost of preparation steps if you just do one thing and then quit, do one thing and quit. So the obvious thing to do is, well, let's do multiple things per worker. But how much? And in what shape? Well, since we're dealing with matrix vector products, it's fairly simple, right? We have a bunch of choices. We could do stuff in sequence, we could do stuff in parallel, or we could use a third form that sort of within each work item does the first entry of the first row of the number of vectors, and the second row of the number of vectors, and so on and so forth. This here, the in-sequence part, helps you amortize any fetch costs. So suppose you were to load parts of the matrix onto the chip in the beginning, then doing more things in sequence helps you amortize that initial fetch cost. Doing this here helps you exploit register space, because, well, you're occupying more on-chip register space, and thereby this allows you to exploit more of that space, because in doing that you occupy more registers. This here just exploits the width of the machine. Well, which of those is better? And in fact, they're orthogonal, so I can do some of this, a little bit of that, and a lot of this. It's not clear, right? You can probably see where all these question marks lead and where the answers come. It's not going to be difficult, just yet. Best work partition is this additional tier of having work groups on top of the whole grid dimension. That gives you a whole another bunch of degrees of freedom that you have to populate somehow. It's not clear what the right choice might be. The same type of decision arises for computing the inter-element fluxes. Why is that? Well, you could also choose an element-wise granularity. You could compute just little parts and then share or only load onto the chip the information across these element interfaces once. And if this element and that element fall into separate work groups, then what happens is that you have to load both of these twice, because they're not shared, because they can only be shared if they fall within the same work group. So the trade-off here is between more data reuse but less parallelism. So if your mesh is not that big, then you might suffer at that. Also, you're limited in how big these guys can get. I made a cute animation here. by how big your output buffer is and how much metadata you can fit onto the chip. Again, it's a question that you don't necessarily want to answer. Another thing that I've said a number of times just now was granularity. So every part of this computation somehow has a favorite granularity. The differentiation has a favorite granularity, the surface integrals have a favorite granularity, and the flux evaluation has a favorite granularity. How do those all match up? Well, here's at least one X. Instead of trying to cater to each individual part's favorite granularity, you make the minimum number. You make a minimal granularity that you can get away with that allows you to just about fill your SIMD with, and just about satisfy your padding requirement. And then you use that, and you enforce that all the others have to choose multiples of this granularity as the basic size of their work group or whatever it is. And well, it's somewhat clumsily in this micro class. The idea for this has also been around for a while. Right. But how big do you choose this guy? It's also not quite obvious. In summary, it's a bunch of difficult questions, and if you're an applications guy, you also don't care about the answers. You care only insofar as you want a fast code, and you don't have sufficient heuristics, and the answers on top of that don't have very lasting value. So obviously, you tune for them, and you decrease in your reliance on what you have to know on hardware values. And I'm glad that Aaron isn't here, I think. Because, oh God, okay, so grill me for it. Right. But it was kind of liberating to shift the emphasis from these tuning results to having to just having to come up with a bunch of ideas or dimensions along which you may be able to increase the performance of your code. Now, obviously, you've seen the mechanism that I've used. That I use for this auto tuning. It's PyOpenCL and PyCUDA. Does it work, or what does it win me? I'll show you. Well, this is an incomplete list of the benefits. Of course, flexibility. I can do automated tuning, and I can be more flexible with more performance in the face of the user specifying different things that I might want to do. So, but well. In a sense, the speed aspect is still dominant in a way. Here's one that's targeted at Aaron specifically. This here is a data set that shows, well, how many given this work decomposition that I showed you earlier, how many things do I do in parallel, how many things do I do in sequence, and the size of the blocks is how many things do I do in this inline parallel fashion. Well, these are the runtimes. The good news is, well, it doesn't entirely matter. Like by choosing at random, I probably land within 20%. If I'm spectacularly unlucky, I can land up there by a factor of 2. On top of that, well, how appetizing is it to model something like that? Can you, Aaron? Well, I can't. Or personally, I don't have a particular case. Of course, you might argue, well, this graph isn't very enlightening in terms of the way that it's drawn. But I couldn't. Mm-hmm. Right, exactly. And I mean, as an applications guy, more or less, my argument would be I have work to do. and that, I don't particularly care what this penalty at 32 and this penalty at 16 might be, and if it's still there on Fermi, I don't know. I'd have to rerun this and redraw this graph. But that's where the lasting value aspect of this comes in. I don't personally gain much by making all these models of long-stripping chips. What I care about is continuous alerting solutions. For me, it's a pragmatic thing to do, I'd argue. Right, so this gives you a glimpse of the performance aspect of it. On the flexibility aspect of it, here's again the variational formulation. Here's this flux term. The flux term from a CS perspective is a bit of an ideal storm because it's something that goes into very tight inner loop, and it's something that the user gives to you. And those two things don't usually go well together. On top of that, it's something that's usually written in a mathematical notation in a paper somewhere. And, well, the user has to transcribe it somehow to make it match your code. This is what you might find in a paper for the flux term, for an upwind flux, to be precise, for Maxwell's equation. This is how you rewrite it for the solver that I'll show you. It's called Hedge. And basically, the goal was to make this and that match up as closely as possible. There are two cross products, and these double brackets represent the jumps of a certain orientation between two elements, and you say, okay, cross the nodal with the jump in the H field, and cross the nodal with the jump in the E field. And if you look at the actual expansion of that in terms of C code, that you never want to see, it's about 6 times this big. Just for this one line that I showed you. And if I get a choice, right? Okay. So that's another benefit, in my opinion. If you have a layer of thinking between the code that gets executed and the code that you have a user writing, and I think that's a non-negligible benefit also of code generation. Yes. It's actually the numpy cross. Yeah, but use whatever cross product you like. Yeah. Right, no, but
You do have a mini language.
I do have a, yes.
So he had to write everything that corresponded to H del in.
Right, of course. I mean, I have to, like, NumPy doesn't know about interior sides of elements, so I can't get around defining that, right? But the objects that you're dealing with here, for example, all this normal and whatnot, those are NumPy object arrays. So I try to stick as close to not inventing stuff as I can. Right, okay, so that's another benefit, right? Latent advertisement code called Hedge does Maxwell Euler Poisson compressible Navier Stokes, runs on stuff, is GPL3 written in Python, uses code generation here and there, and I hope that by using an OpenCL backend I can just unify the two and probably get done with much less code. Right. Been talking for a while. Question is, how well does all this junk even work? And this is also to try and justify all these people, or to try and explain, to try and show to all these people who've been saying, Pi anything with the GPU, does that go fast? Can I write high performance codes with that? Yes. Yes, you can. In what sense? Well, so this shows you gigaflops per second versus polynomial order. So of course, yes, as you dial down the polynomial order, you get less computationally intense. So you use also. Well, you can do. It's possible. So finite volume codes do better at this very low end because they're optimized in a different way. It's not something that we particularly care to do. So this low end is okay to us. What we really cared about is this chunk here between say 3 and 5, and so we have another code that just implements that implements a simpler scheme where you just do one element per work group, and that does pretty much the same up here at the high end, but all these fancy things considerably save performance in this middle ground. So and that was important to me. How good is this performance? Well, the other code was tuned by hand for the performance here at this high end, and we do considerably better here, and we do just about the same up there. How do we do? Well, yeah. Thank you for asking that. Yeah, yes, we do. Yeah. Right. So this here is on. I think this was it's a GTX280. This here is peak memory bandwidth, and we don't just hit it, we exceed it.
Oh, fantastic.
Yeah, so you're looking at this graph and you're like, here in India, this goes above T. And I think it's, well, we use texture cache for some stuff, and I talked to an Nvidia engineer, and he says it's kosher. It can be. It's plausible enough. Unless there are any Nvidia guys in the audience who want to contradict that. I see that too, right? It goes right above there.
What actually happened? Why are you doing this?
Well, there are a number of things you'd have to consider. Well, we're clearly dominated by these matrix products, right? Right. Well, we should be computationally bound, right? Yet the on-chip memory is just not enough to store all the working sets. So we have to keep fetching and refetching little bits of the matrix, and that's why we end up being bandwidth bound, unfortunately. So far. And yet, since we're in some of these cases, we keep pulling the matrix through the texture unit again and again and again and again. That's where we get this reuse that bumps us, in my opinion, above the peak bandwidth. Right. Morally off chip then. It's not something like this texture cache we don't have immediate control over. We can't measure very well besides measuring effects like that. We're just squeezing. Yeah. You could say we're squeezing the last bit of on-chip memory out of the chip that it has.
So, let me see if I remember. But I thought there should be a part of the computation that gives DGEM
right.
But small.
Right.
And I think if you had big stuff, if you had 1,000 by 1,000, you could get DGEM does not achieve its capability for these 1,000 by 1,000.
Right. Exactly. Yeah.
And so you're down here, so part of it should be giving away.
Right. Yes. If we put in all the fancy bits they do at the very large end, the problem is this very high end, like starting order 6 or 7, we stop caring. We don't put in all the fancy bits that you need to be good here, because our time step goes to nearly 0. So we're not making that much progress.
Yeah, it's still pretty close. I mean, 250 is like
that's a quarter on 280.
I thought on my 285, I think the peak throwing out a special function unit is like 660. Right?
Okay.
Yeah. So this is like more like 240.
Oh, okay.
Yeah.
All right. Fair. So yeah. Another thing that we tried, at least when we were initially doing this stuff, is let QGlass loose on the same matrix product. It was comical. Nobody tunes for like short square matrix times very fast, very short. Nobody tunes for that. You'd think these canned DGEMs are the answer, except comical story also on the CPU. You do a trivial triple loop matrix for this type of stuff. You easily blow Atlas out of the water.
Sure. Although there is one thing that is
Okay, I haven't tried that.
In their paper they talk about doing stuff.
Yeah, okay. We tried Atlas, and it's hard to believe that simple triple loop could do that.
There's a paper by a guy in Dodo about doing a nice
Right, and Goto is recently open source, I think. Yes. Okay, sad. I thought it was BSD. Okay. Okay. Well, all right. Anyway, so yes, we do hit for the two things that do dominate our runtime, which is surface integration and differentiation. We do hit memory bandwidth for stuff like assembling vectors together and gathering the fluxes. This here is a much more scattered operation, so we don't manage to do just that. Does it work in parallel? Yes, it does. This here is 16 GPUs versus 64 CPU cores. Now I'm not being fair to the CPUs because these are double quad cores of the Core 2 generation. So they're seriously starved for memory bandwidth. So the more I add on the CPU end, the more cores I add to each machine, the better I look on the GPU comparison. so no, this is bigger Flux across the whole aggregate machine. So I might as well have done 16 cores here, and it wouldn't have looked too much different. Right. Yes. But I don't even like CPU performance comparisons too terribly much. Yeah. That's right. Except I generated these numbers like a year and a half ago. Yeah. Right. So for all practical purposes, just forget the CPU. That's what I say. We need comparisons. I mean, somehow the most meaningful thing is to compare against theoretical peak of what a CPU could potentially do, and then it's up to each individual person to get disappointed by what it actually does. Right, and the same standard, in my opinion, is showing gigaflux per second, showing absolute performance rather than yeah. No, this is what this does. The dollar is too variable. No. Okay, yes. Yeah. Right. Okay. Fair. Sure. Yes. That would be the ideal world. Right. Okay. So anyway, 16 GPUs. North of 3 teraflops performance, smiling face. And if you could, one thing to note, if you compare this picture to the single GPU picture, you know that you notice that it doesn't arch upward just as well. So there's probably some potential to get this higher up, but you know, at the high end, at least you do get the tops. Right. This here is single precision versus double precision. It's just one of those slides that you need to convince people that double precision is not such a horrible thing to do, even if you're on the GPU, but I don't need to convince you. Then some other stuff that's more numerical in nature, we do viscous shock capture. Based on, we get good performance on linear conservation, also when we try something non-linear. This is just a simple advection equation, and the phenomenon that we're combating here is that you get these little wiggles. In an advection equation, that doesn't matter. But imagine that this here is, say, a density, an Euler equation, and it wrinkles below 0. All of your computation dies in a second. And you can be sneaky about it, like, okay, fine, performance. And as soon as you do that, well, you get visually pleasing answers, but you also get answers that are wrong. So why not mess with the computation at least in a more mathematically well-defined way? And if we do that, we get that. How do we mess with the computation? We simply add this diffusive term. Now, obviously, you don't want to add uniform diffusion. So the part of all of this that we're trying to market here is a detector that adequately controls where to work with high diffusion and where to leave distribution well alone. I don't have time to tell you all about the details of the detector. The basic idea builds on work by Galerkin in 6. And questions that we're trying to answer is how do you make this thing suitable? So there it is perfectly local, but it is not. It doesn't detect as well, and it needs lots of dialing around with the knobs, and we try to make it reproducible and still retain locality. What do you do about time integration, and what happens with actors? And well, I can just show you a very short stuff here. So we apply this to Euler's equations at 1D. This is Plot's problem, one certain test problem. This is another test problem. Shock wave interaction in minus vertical the Schwarzschild problem. And this is generally used to advertise high-order methods, because low-order methods generally completely botch because of the interaction between the shock and just the wave path. Also works in 3D. This is flow against the separate channel. The emergence between the flow side. Also, since movies are always pleasing to look at, well, here's a movie of the flow in the channel hitting a square obstacle, and here's what you see in density. This is Reynolds number 100, Mach 0.1. Here you can see some blob that I used to just nudge it into getting unstable, and then the flow starts shedding vortices on it. And other applications that we can do is obviously I've shown you Maxwell, so we can do full planes in a couple of hours. How correctly, that's up to debate, but argument I'm trying to make. Well, okay, you've seen most of the stuff. You've seen PyCUDA, PyOpenCL Hedge. There's an article on this. There's an article on this runtime generation. What I've been trying to say to you over the past couple of days, GPUs and scripting work surprisingly well together. With runtime code generation, you get multiple benefits that I've been trying to show. GPU DG, also a pretty good idea, in my opinion. And there's certainly stuff that can be done. For example, how do you integrate this with curvilinear elements without losing all performance? How can you make the time stepping less painful? And well, I've shown you some of the shock action work. That's all for my part. I'll be seeing you in the labs this afternoon.